Hello and welcome to our short tutorial series, this time figuring differential equations. In the other lectures I explained to you what are important, and the importance of being able to build a differential equation based on concepts that you learn from basic science. And this applies for everything. And we are now dealing what we call the ordinary first order differential equation. And we already gave some examples. We told you how to solve. And I would like now to bring some more examples for you. So before we go to new topics in differential equations, I would like to give some more examples on the first order ordinary equations. Okay, if you remember well, ordinary equations are equations that the function I'm looking for depends on only one variable. All right. So I'm going to give another practical example now. This practical example is a very interesting example. Everybody already made the experiment of cools down some hot object, throwing it in water, in a bath, in a tank. And that's what I'm going to do in this practical example. In this practical example, I'm going to get a sphere of copper. Why copper? I mean, because copper is a nice metal, very well. It conducts very well heat, so it's always going to be in some temperature. It's very hard to produce gradients of temperature, variation of temperature within a small copper object, because it transfers heat very fast. And I take this sphere of copper, I heat up to 100 degrees C. So I have this sphere, I heat up to 100 degrees C, and then I throw it inside a bath or a tank which has water at 30 degrees. The tank is very big. Okay, I'm going to heat up almost nothing in the tank. I consider the volume of water much bigger than the volume of my sphere. So I consider that the temperature of the water will be like 30 degrees forever in life. And I want to know, of course, how long it will take for the sphere to cool down, because it's going to give heat to the sample, and I want to know when I can go there, get my sphere cold enough for me to deal with, because that's why I throw the sphere, hot sphere, inside the water tank. Okay, so there is one observation I made, that after 3 minutes passed after I throw the sphere in the bath, I know that the temperature is 70 degrees C. So this is a given fact to us. Somebody gave us this measure and gave us this fact. And we want to know, but how long I have to wait until the temperature is like close to the 30 degrees? I put 31 degrees C. So how long I should wait? So the problem is very well established. And you know that this is a problem of energy transfer, or transport phenomena involving energy. Hot object giving energy to a bath. This is very common and it happens inside our body all the time, right? Okay, so we needed to construct a differential equation for this, because we want to know the variation of temperature with time. And the variation of temperature with time, as you know, the establishment, we could go for many things here, and there are many laws of heat transfer. And I'm not going to elaborate on the heat transfer laws, but I'm going to go and get a very well fact that says that the flux of energy that goes depends on the gradient of temperature in a stationary regime, right? And this is means that the variation And the flux depends on the difference of temperature between the hot and the cold. So I put the two informations in here that I know from heat transfer. And basically that the quantity of heat that will be transferred, which is the quantity, the time variation, which is the flux of heat, it's proportional to the variation of temperature between the object and between the hot and the cold part. And the second information is this is also proportional to the time variation of temperature. We learned this in transport phenomena. So we can build up an equation that the time derivative of the temperature of the sphere in any moment has to be proportional to the temperature, the cold temperature, which is the bath, the water, and the moment, the temperature at that moment of the sphere. So T minus 30. T is changing with time, of course. This equation is saying that. But it's saying that the rate in which the temperature is changing is proportional to the delta, because that is proportional to the amount of heat that will be transferred between the sphere and the bath. Okay, we may have another short tutorial on heat transfer sometimes. But anyway, I was able to put together the equation. So the equation tells me that in any moment, the time variation of the temperature has to be proportional to the difference of temperature. And I kept the bath at the constant temperature. So the difference of temperature always going to be the temperature of the sphere minus the temperature of the bath. And of course, the temperature is decreasing, I know is negative, and there is a constant here. That's a constant of heat transfer. This is something related to the property of the medium able to take. If I isolate the sphere, if I put it not in water, but if I put in oil or anything else, that may change this constant, okay? I know this constant. I know that's a constant. And I'm going to use the boundary conditions to get the constant. I'm going to use that after 3 minutes, the temperature is 7 degrees to find that. This is a typical example that I can separate the functions. I can send the T minus 30 down here and the dt up here. So I separate temperature from time. And then I'm going to have that the variation of temperature normalized by the difference of temperature at any moment is proportional to the time variation. So I have that dt over T minus 30 has to be minus k dt. T temperature, T time. And of course, now I can integrate this. Is an indefinite integral. It is not with limits, so I'm going to end by having a constant. But the integral of this, you can do easily, because you know that in t equals to 0, I start in 100 degrees. So in t equals to 0, I have 100 degrees. So I can integrate from t equals to 0 to t. I integrate from 0 to t, and this will be from 100 degrees to some temperature, T capital. That's the integration. I think I should put another color, right? Because now I can make this integration to be 100 to t, right? I start in 100 and I'm going to end in t. And how long will it take? The time will pass from 0 to t. Then I can remove this constant because it's going to be 0, because I already defined the integral. I input some of the boundary conditions, the initial conditions, in the integral. I can do that too, and that's why I correct it here and I did this way instead of other way. Then when I do the integral, this part is the logarithm of t minus 30 divided by 100 minus 30, that's 7. And on the other side of the equation, minus kt, because the integral k is a constant. And then I can invert the log, and then I end with the solution. I end with the fact that the temperature in any instant of time is 70 times the exponent to the minus kt plus the exponential of minus kt plus 30. When t equals to 0, this is 1, I recover the 100. So there is always one step in solving differential equation, which is test for the conditions you know. And this is fine. But I don't know k is a property of the system. But somebody was smart and made a measurement and gave it to me that in 3 minutes after the sphere is in contact with water, their temperature gets to be 70 degrees. Then I put here 3 minutes, 70 degrees, and I solve this equation. This is this equation. Simple to solve it, because this will be 70 degrees now. And then when I do that, the only thing I do not know is the constant k. And I can extract the constant k that now will be 0.186 minutes minus 1, because I'm using time in minutes. Right? Therefore, the overall solution, now in ready to highlight, right, is that the temperature is given in any moment as an exponential with exponent minus 0.1860 and t expressed in minutes plus 30. And then I can ask, when t is equal to 31, what is time? And then I find the answer that when t is equal to 31, I pass it here, this is 1, I take the logarithm and find out that the solution of this equation is t, or the solution of the question of my problem, is t equal to 23 minutes. So you see, I construct an equation, I did a little different, I know the condition, so I impose the limits of the integration, which is a true fact. You know, the sphere is going from 100 degrees to t, when the time goes from 0, the initial time, to t small t. And then I get everything else in this problem. That's very nice, isn't it? Well, this practical problem brings me to make an observation for you that helps a lot, because exponential is something that appears all the time. All the time we have exponential in differential equations. So always you have an equation like this, a homogeneous equation equal to 0, that says that the variation of the function plus a constant time in the function itself is 0. This function necessarily has to be exponential. It's easy to prove this, right? Because I just move that way, make the separation of equation, integrates, and I get. So always find a differential equation like this. You know that the solution must be exponential. Okay, now, what's happened when we don't have a homogeneous equation, but we have a first order? Everything is like that, but it's not equal to 0. It's equal to some function. You can do the same. You know, you can invert. This is a little more detailed to do, but you can show that, well, the solution of the homogeneous will be there because I have a constant times this is the solution of the homogeneous, plus the solution of the non-homogeneous, given by the integral to some limits, or you don't need to put limits, you leave for a constant to be set as you have the later on the boundary conditions, but this is the solution. The solution is always, you know, the homogeneous plus the non-homogeneous. And this is given by this part. And we can prove this. I'm not going to do, because this is only a tutorial, but you can do as an exercise, right? And basically you have the solution, the exponential, times the integral of this function that appears here that makes the equation non-homogeneous, times the exponential, integrate. You just integrate. Actually, normally they say that's b divided by the solution of the homogeneous, but the solution is exponential in this case. And this appears a lot of times, so it's nice to know this. And if you know this, and you can prove once, you know the solution forever. And this is something that I'm going to tell you later, that when you have a non-homogeneous equation, always you're going to solve by having the homogeneous solution plus a non-homogeneous. And here, if you multiply by the constant, this is the homogeneous part, solution of the homogeneous equation. And this one always going to be the solution of the particular or the specific function. Okay? So this is also very nice to know. And if you know that, that saves a lot of time when you're solving equations of first order of this nature. And this, believe me, is a lot of equation has this type of format or this type of shape or this type of dependence. It is always kind of first order, non-homogeneous, but it comes from a homogeneous, and you can show, because you know this solution, when I put in the equation, will make this part 0. So the derivative of this, if you see, will give exactly b equal to b. So I'm already giving the proof that I ask you to do as exercise. So I'm asking you to do as exercise this proof, which is simple. And if you're not, you can write to us. We're going to provide you the proof. But this is a very simple proof. And this is a very interesting thing to have in mind, because it saves a lot of time. And once you do generic, you can always do a lot. Because many people solve equations, you know, by trying, by making a choice and see if that's true. If it makes the equation true, we know that the solution of any differential equation is the function that makes this a true fact. And this, I believe, I can guarantee to you that makes it a true fact. Okay, very well. So this observation is important for you to keep it. But let me give you some examples of other things that we can do in this separable functions method. You know, suppose I'm dealing with a phenomenon that has a little more complex equation. This is a little more complicated. You know, I was there, I built up an equation that represents some phenomenon. And this seems that 2 times x times the function that I do not know, y I do not know, minus y squared times the derivative of y with respect to x minus y squared plus x squared equals to 0. That sounds awful to solve, right? And this is, the fact that appears square here is not breaking down being a linear. Remember, I explained to you what's a linear and a nonlinear differential equation. Okay, now pay attention, because sometimes you can do some operation that will provide ways to make a substitution of variable that make the equation easily solvable. This normally is called substitution. It's another method. You're going to change variables. Always works well. Let's take this equation and divide. I'm going to use this example to explain to you how you do. Let's take this equation and let's divide by x squared. If I divide this equation by x squared, here I get 1. Here I get y squared divided by x squared, that I put everything in square. Here I lose 1x, but I have y over x, 2, blah, blah, blah. And dy dx, I cannot do anything. You see that everything is appearing x over y, y over x, sorry. everywhere is appearing y over x. So I'm going to call y over x as a new variable. I'm going to call u. And I'm going to make a substitution. But to do the substitution, I have to find out what's the relation between dy dx with du dx. So du dx, you all know how to apply the derivative for a ratio of two functions is equal to the derivative of y with respect to x times 1 over x plus y times the derivative of 1 over x, which is minus 1 over x squared. So there is no 2 here, sorry. Right? It's 1 over x squared. That's the derivative of this expression, and that's going to give us a relation between dy dx and du dx. So if you invert this, you can come and put in this part of the equation. Here everything will be u, and here you're going to substitute by something that has du dx. When you do that, you can find out another equation, now relating u with x. But see, now it's easy because now I have only x here and everything else is u. So I can separate again. This equation, I can rewrite it as this equation. And then I can solve now this equation. And once I solve, I'm going to get u of x. But u of x is nothing more than y of x divided by x. Therefore, I can obtain the y of x. Right? Then this is a very important type of argument that we use all the time. That's what we call redefine some variable. And sometimes, why I have chosen this example? Because sometimes you have to choose variable that's not only depending on x, it's depending on both. And then I change the aspect of my equation by combining those, right? And make the substitutions. And then I transform this equation that was awful in an equation that's easy to deal with. And the integral of this is not hard to do. You just call u square as alpha, and then u du gonna be d alpha, and you solve the problem and you have the solution. Easy. Then it's a problem of integral, right? Which is much easier than the differential equation. Okay, so this was another example. Very nice. Now I want to give you another practical example. And the practical example, you know, in biomedical engineering, we use a lot of electricity. And circuits are there all the time. And I'm going to consider a resistive and inductive circuit, RL circuit. Has a resistance and has an inductor. And we all know that we have this circuit, you apply a voltage, the current will have a response. We have a timing response. Because we know from the electromagnetism that if I try to create a magnetic field in the inductor, there is a reactance and it has time to build up. If I come and use the Kirchhoff type of law, I can know that the differential potential that goes across the resistor plus across the inductor has to be the total applied voltage. So I can build up, using those principles, an equation. And this equation relates the time variation of the current that is going to circulate in the circuit with the properties, the induction and the resistance, and the voltage that was applied. That here I put generic. I put as a voltage that will depend on time. Right? Now I have to solve this equation. And well, this is an ordinary first order differential equation, and I have to solve. And I'm going to consider two different conditions. I could directly apply what I told you about, because this is exactly that equation. Divide everything by L. If I divide everything by L, you're going to get exactly the equation that I give you as an equation that's going to appear 100,000 times, right? Where this is the function I'm looking for, variation with time. This is the function itself. So this plus this is a function, independent function. Remember, this is exactly like this. Exactly like this. This constant is R over L, and this constant is the voltage divided by the inductance. It's exactly. So you could come and put the solution. But I'm going to build up, so again, it's easy, so let's do it. And when we do it, we have this equation. And as I explained to you, let me put side by side so you can identify. I have this. So this equation has this solution here, right? Okay, I'm going to simplify this by just putting the solution. That's the solution. That's the solution of this equation. But there is an advantage, because b is a constant, it comes out. And the integral of exponential is exponential, it's easy to do. Now, the value of a is r over L, and the value of b is v0 over L. And then I have the integration. Easy to do. Just apply what I told you. Right? And if you apply what I told you as a generic solution, you end by having this. It's the solution of the homogeneous times the solution of the non-homogeneous, plus a constant. But this we already saw that b is a constant, comes out. And I have a condition, an initial condition, that when I connected this circuit, there was no current there. So in t equals to 0, the current is 0. Therefore, the integral of the exponential is the exponential. This is a constant, comes out. And this exponential is nice because give you r over L t. And this will cancel, so give you 1 minus the same r over L, it's 0, it give you 1, but then comes this minus 1. And then you get the famous solution of the circuit, the resistance with an inductor circuit. And we know this is a curve that's 0 at t equals to 0. T equals to 0, this is 1, cancel, and goes. And when t is very, very big, this term disappears. And this is a final value, which is basically the voltage across the inductor. Right? So this is a nice practical example of what I told you as a generic example. But this is not everything, right? Suppose now that V0 in this equation, we are dealing with the same equation. That's the equation. But now here I assume that V is a constant. There is no time variation. But now I want to impose that V actually oscillates in time following a sine function. Therefore, my B of t, generic, is a function that is V0 sine of omega t divided by L. So V0 still come out, but now I have the sine of omega t. This is omega, right? And I'm going to integrate. Normally the integration I put as t prime, but it's the same t. Those. If you know what you're doing, there is no problem. And then I just do this integration. And the integration of sine time exponential is a well-known. You can go to tables or anything. And what we get? We get a solution for this time oscillation, a oscillatory part, normally with the same dependence of the... You see, that's one very nice thing about this. Always, this part will have the same dependence of this part. So, always this term that's going to appear here has the same functional similarity with the term that's the non-homogeneous term of the equation. And here it is. You have something that's sign-dependent, will appear something that's sign-dependent. With some numbers appear here because that's coming from the integral. And then we have a solution. When I put oscillatory in the LR circuit, you have an oscillatory part, we know that part, and then we have a part that decays with time. So as the time goes, this term disappears, which is the decay, and then you have an oscillatory one that will oscillate, characterizing the very famous oscillation of the inductor and resistance circuit. Solution here. This is a nice transparency to keep. You have an equation like this. This must be the solution. And if you learn how to deduce, you're never going to forget. And then you know exactly how to propose the solution in a very fast time. Okay, so just to finalize, suppose you have now, I teach to you how to solve when this is a constant. This gives exponential. When this is not a constant, we can prove that when this is 0, which is the homogeneous equation, the solution, actually the exponent, is the integral of this function. Another important example, and this you can do by separating variables too. Take this, put it here, paste the y here, put the dx there, and integrate. Easy to prove. I prove it already in words for you. Right? Good. So this is a most general equation. Right? It's a first order ordinary differential equation which has the derivative, then a function of x multiply y, and an independent term which is another function of x. And I already told it to you, if r equals to 0, this will be a homogeneous equation. The solution is basically the exponential, but the exponent is the integral of this function. Okay? Very good. Now, what I want you to do is do what we call proposing solution. We're going to propose that the solution of this must be the product of this, because what we learned from there. And when you propose this, you can come with this y and substitute in this equation. And when you do that, you end with another equation. But now this other equation is something very interesting, because you see, it has v, u, and r. And if I divide everything by v and define du, I can end, because u, remember, right? Du dx is equal to this. But this here, the v solution is the solution of the homogeneous. So this is 0. So when I propose this solution, I already know that I know v. Now I'm going to say, well, v is the solution of the homogeneous when this is 0. But then let me propose that the product of a function that I do not know times the solution of the homogeneous equation is the solution. And when you put that in the original equation, it turns to be those terms. But it's very interesting because the term, the homogeneous equation appears there. V is the solution of the homogeneous equation. So this is 0. Disappear. And I end with an equation that says that du dx times v equal to r. Oh, du dx is equal to r of x divided by v of x. And then I integrate. I just integrate. And by doing this integration, I have this total solution. So then I end with the total solution. This is a very interesting method to solve the equation, and you can apply in many exercises. Let me repeat to you. I have a first order equation that's like this. right? But I know, I imagine that this is 0 for a moment. So if this was a homogeneous equation, it has 0 here, right? That will be the solution. So this is the solution of the homogeneous. Normally we call H. And I call the solution of the homogeneous V. And I know that when this is V, this is 0. And then I propose that V is part of the solution. But V times a function that I do not know, that's U, is the solution. And I substitute this in the original equation. And when I do that, this equation is oversimplified, because when I substitute, that's going to appear derivatives of U with respect to x, but going to appear this term here, that I know that this is the homogeneous equation, because V is the solution of the homogeneous equation. So this term gives you 0. And then this whole equation now reduced to du dx equal to r of x divided by v of x. Right? Just divide here. And then I do the integration, put x in the other side, integrate, and I have the overall solution. Another nice method for solving the ordinary equation of first order. Well, with this lecture, we basically ended this short tutorial in differential equations of first order. In the next lecture, we're going to start to increase the order. Second order differential equations are also very important in many situations, so we have to learn how to solve. Okay? And then at the end, we're going to touch a little bit the differential equations. Bye-bye.